So I'll try not to be long. First of all, what I will show you now is the work of many institutions and such, despite the logos not being here. I'm sorry about that. So I don't normally work a lot on muscle. It's some new adventure that we got into, so I'm learning. This conference has been great. I learned a lot. During this process of learning, especially in this particular case during the COVID pandemic, I found out about the vascular occlusion tests being used to extract a lot of information. So last basically whole day, we heard many, many things being extracted from them. In the particular case of the people who are in the critical care, intensive care world, they use these notations. So they look at the deoxygenation rate, DO2, reoxygenation rate, and oftentimes they look at the area under the curve. Already from Farouk's presentation earlier today, you saw that we also look at the blood flow index. We can get both its baseline values. We can also do things like area under the curve. How fast it decreases, etc., is not so important because we are physically occluding. You just want to do that really fast. As I said, we entered into this adventure through the door of the critical care, in particular during the COVID pandemic. I was told by an intensivist in a meeting in December 2019 that he put mNIRS probes, and he even worked in the development of a commercial clinical mNIRS on the thenar muscle, because thenar muscle has a lot less variability. There's a lot less fat over it in these patient populations, and they can put the cuff much closer, so the much less amount of body is cuffed. Patients are more comfortable, etc. During COVID, I sent him an email saying, you must be going crazy during these lockdowns and work. And he told me something, which is an anecdote I often repeat, because for a physicist like me, this is interesting. We got into this adventure of looking at muscles as an indicator of well-being in critical care. He said, I like three things in life: research, my clinical practice, cycling, and research. My clinical practice is killing me. I'm not allowed to go cycling. In Spain, you are not allowed to take even walks for the first parts of the original lockdown, so let's do some research. And then we got a dozen portamons from Martinis, and we went into a worldwide study called COVID-19, and then we got it. And during that process, I started to learn that they could use this information to monitor hemodynamic status during resuscitation. So they have an idea as a prognostic tool when to stop fluid resuscitation and things like that. They can use it during cardiovascular challenges, such as weaning from ventilators. It has a predictive prognostic capabilities about failure from weaning from ventilators, and the measure of endothelial function. And then he said that this method is good. Prognostic value is well shown, but it lacks translation into clinical practice. And one of the problems was the lack of standardization. Protocols were different by different people, durations and type. I noticed here that this was also an issue that was discussed. Different analysis methods were used, how this information was extracted. Different types of cuffs were used, different locations were used. And in general, especially for a clinical population, not the population in this audience, for the intensive care clinic, lack of integration was an issue. They were using CW mNIRS clinical devices, not the ones that we see advertised here, the ones that exist in clinics. They were measuring only oxygenation, so this led to a lot of issues, replication issues, high variability, and usability. Here's an example study. In this particular study, they looked at the influence of measurement size, probe sizes, and deflation thresholds, because they were trying to deoxygenate people up to a certain level. And they showed that there were statistically significant things. Also, they showed operator dependence, hardware dependence, lots of variability. That's not good. Another master thesis looked at the three clinically available devices, the InMOS, the Foresight, and the NIRO. Some of these have been replaced by newer models. These are the devices typically clinicians use to look at the brain during cardiac surgeries. Neonates are monitored, etc. And then the results from a vascular occlusion tests were statistically significantly different depending on which parameter you extracted. So at the same time, European Union had put out a call for a European project for the emergency funds for the COVID-19 pandemic. And then we put in a proposal where we said that we want to use this to stratify patients. At that moment, it was still the time period before the vaccines were introduced. So the intensive care units were filled with COVID patients, and they wanted to wait to stratify them according to outcome. And based on a paper related to ARDS, we said we can take some steps towards it, and we can also help them to target certain things. We knew that the vaccines were coming, so we were actually targeting the general ICU population. This project was interesting. It involved industry. You see mNIRS name here. They are one of the sponsors of this meeting. They have their devices there. They are our colleagues from Polytechnico, developers of the technique. We had a company Splendo, somehow related to Artemis at some point as well. They are data integrators, machine learning people, standards, and us. So we tried to make a device. This device combined time domain NIRS. Yesterday, Michele gave a good presentation about that. Basically, it allows much better measurement of the absolute values of oxygen saturation, blood volume, and tissue scattering. And then Marie gave a good introduction to DCS. Already DCS allows the measurement of blood flow. We combined this with a clinical pulse oximeter and an automated tourniquet. And then we started to extract information about baseline metabolism. The device is still a lab device. It is a 19-inch rack, so it's not tiny. It's more like the devices we were showing from earlier years, but it's got a lot of things in it. It's got basically these two methods in it. It's got a smart probe. This probe is not only acts as a safety measure for turning off the laser if it's not in touch with skin, but you can also normalize the amount of pressure you apply on the muscle, because you can imagine the moment you start to press and you have a very sensitive blood flow measurement, you're changing blood flow. It's got acceleration detection, orientation detection that you can look. It even has a light detection. Comes with this box, which is not necessary for its operation, but we use it as a quality control. We have now 5 of these devices that have been used nearly for 2 years, and we are monitoring them day to day for variability. You can click hardware buttons so the nurses can do it. It was made during the height of the COVID, so it was made for operation, all fully automated operation, minimal amount of touch. You don't need that screen that you see on the top, etc. It is made for doctors, so the clinicians can operate it. It's one of our first devices that we actually gave to clinicians and didn't need a PhD student or a postdoc to be there. We validated its basic performance, which is what we typically do. We looked at accuracy and precision, but then we did a lot of usability work. So it is still not at the grade of what you see outside here from commercial machines, but it's been tested about more than 500 sessions of measurements by clinicians, and we recorded how many times it failed, etc., etc., etc. As I said, it allows us to measure these two parameters together. And due to the short time and me focusing on just the device, I'll highlight one point here. One is that in this particular literature, they extracted what they call NIRVO2, very similar to other metabolism measures used here, with the slope of the deoxygenation in the first minute. And they sort of normalized that by the change in the total hemoglobin concentration during this period. In fact, that is almost minimal and irrelevant if you work closely, but there's a tiny bit that is there. And we sort of waved our hands and made the assumption that the models used to measure the metabolism in the brain from the knowledge of tissue oxygen saturation, muscle oxygen saturation, whatever you call it, pulse oximetry-based SpO2, and the blood flow index to have an MRO2 estimate, a metabolism estimate from the baseline data. Okay? And then we did the typical things. We looked at the reoxygenation slope, area under the curve in BFI, and then used this as a measure of the global hemodynamic status of the patient. What Sienna showed earlier could also is an interesting thing, and we see a lot of confounders from all the secondary things that these people had. A typical data I will show you later, but in the meantime, we also compared this to INVOS. So the people were using INVOSes because that's a clinical device. Again, it's not a device made for muscle, but it's in the clinic. It's a lot easier for the clinician. They don't need a separate ethical approval. You see the blue line by INVOS, part of this is due to the difference in time domain spectroscopy and CW. Part of it is the black box algorithm of INVOS. INVOS tends to overestimate the deoxygenation. It's got these like sharp lines, and then it has got a huge increase in the hyperemic peak, which I believe is not right, and then it clips it. So if you look at a Bland-Altman plot, it's patient dependent, it's value dependent, so they are not interchangeable. I'm not gonna say INVOS was wrong. I'm just gonna say from physics, from phantom test, from our knowledge, time domain spectroscopy is better than the type of CWs mNIRS INVOS does, and INVOS works for certain clinical applications, but for this, it was different. From the first phase one, I also show you really quick results. This is a typical result that you see. Septic patients show similar deoxygenation, blunted hyperemic peak, delayed recovery, and then we see statistical differences. This is general ICU population. The full analysis is yet to be done. Yet there are statistical significant differences. In blood flow, this hyperemic blunting is extremely obvious. Huge hyperemic peaks in healthy subjects with almost no peaks and oscillations in sepsis patients. Again, group level differences. And then looking at this MRO2 from this complex population and combining it with some healthy subject studies, different colors are different muscles and different devices. It does look like, and then we need to understand the outliers a bit better, that the MRO2 during baseline can be a predictor of the typical cough-induced deoxygenation and oxygen metabolism that you measure by CW NIRS or time domain NIRS. If we prove this to be correct in general, now we are looking into it more carefully, this will allow us to measure MRO2 continuously without the need for doing cough occlusions. And this needs to be further explored. So at the end, I showed you a device which was the work of a very large collaboration. And this was my main take-home message, that now blood flow and oxygenation measurements are possible, even on the muscles. Yes, during motion, blood flow measurements are still problematic. Various ways exist to try to correct for them. Many people are working on it, but before and after exercise or with this type of VOTs, we have very nice devices that could also be automatized. And I know this is not a brain meeting, but I'll send with an advertisement of an upcoming meeting where we talk about brain from subcellular level to the diffuse optical level that's coming up at ICFO. Thank you.
Thank you, Noor. Question.